Hi, I'm Steinar, and today I'd like to present Alan Turing's groundbreaking paper, Computing Machinery and Intelligence. It was published in 1950, and the paper laid the foundation for what would later become artificial intelligence. Today, we'll explore Turing's key ideas, his methodology, and how his vision relates to modern AI. Alan Turing was a British mathematician, logician, and computer scientist born in 1912. During World War II, he played a crucial role. He built a computer that could decrypt encrypted Nazi communications. This is considered to have significantly shortened the war. After the war, he turned his attention to the question of machine intelligence. Computing Machinery and Intelligence was published in the philosophy journal Mind in October 1950. What's remarkable about this paper is that it was written at a time when digital computers were still in their infancy. Yet Turing foresaw their potential with extraordinary clarity. The paper's central question, can machines think, effectively launched the field of artificial intelligence. Here is the outline of my presentation. It directly follows the sections of the paper. First, the imitation game, later known as the Turing test. Then, critique of his new way of framing the question, can machines think? In section 3, Turing describes the machines concerned in his imitation game. 4 describes the architecture of digital computers, which remarkably still applies today. In chapter 5, Turing describes the theoretical aspects of discrete state machines. 6 is, in my opinion, one of the more interesting chapters, where Turing addresses objections to the idea that machines can think. And the final chapter, Learning Machines, which remarkably predicts modern machine learning and artificial intelligence. Turing begins by questioning the very phrasing of "can machines think?" He points out that the terms machine and think would be too ambiguous and difficult to define clearly. This slide shows the opening section of Turing's paper, where he acknowledges the difficulty of the question. His solution is to replace this philosophical question with something more concrete and testable. This move is classic Turing, finding a practical way to approach an abstract problem. The imitation game. Here, Turing introduces his famous test, later known as the Turing test. To frame the setup in a relatable way at the time, he proposed this. The setup involves 3 participants, a man, A, a woman, B, and an interrogator, C. The interrogator's task is to determine which participant is a man and which is the woman through a series of questions and answers. He then proposed switching the man with a computer. Now, the test involves figuring out who's human and who's the computer. Communication happens only through text, eliminating physical cues. The point of this was to replace the original question, can machines think, with can machines successfully imitate human responses well enough to fool a human judge? Turing's genius was in creating an operational definition of thinking based on observable behavior rather than internal processes. In the next section, Turing anticipates criticism of this approach. The highlighted text shows his argument that the test effectively separates intellectual capabilities from physical ones. The sample Q&A exchanges demonstrate the kind of interaction that would occur in the test. Note the machine's human-like responses, including admitting inability to write poetry and taking his time to calculate a sum. Turing addresses a key criticism that the test might be unfair to machines. They might think in a way fundamentally different from humans. He acknowledges this as a strong objection, but argues that if a machine can pass the test, the objection becomes less relevant. This section shows Turing's thoroughness in considering potential challenges in his methodology. In section 3, he narrows down what he might what he means by machine in his thought experiment. And as the highlighted text shows, he decides to focus specifically on digital computers. This restriction, which might seem limiting, is actually quite forward-looking. Turing understood that digital computers had the most potential for the kind of capabilities he was discussing. He's not asking if existing computers of 1950 could pass the test, but whether imaginable computers, future machines, could do so. This distinction is important. Turing was projecting decades into the future. He's effectively saying, let's focus on this class of machines and see how far they can go. This section provides Turing's explanation of how digital computers work. The highlighted text gives this definition: machines that carry out operations a human computer, meaning a person who computes, could do. He outlines the three key components of a digital computer: the store, memory, the executive unit, which is a processor, and the control, what we'd now probably call a program. The diagram on the right shows a modern representation of computer architecture, which remarkably aligns with Turing's description. Turing was essentially describing the stored program computers that would become the standard architecture for decades to come. Remember, this was written when most people had never seen a computer, making his clear explanation all the more impressive. This is perhaps one of the most important theoretical sections of the paper. Turing explains that digital computers are discrete state machines operating in distinct steps rather than continuously. The highlighted text introduces the crucial concept of universal machines, computers that can simulate any other discrete state machine. This is what we now call the universal Turing machine concept, which he had developed in his earlier mathematical work. This property means that in principle, a single digital computer with enough storage and the right program could do anything any other digital computer could do. Turing reformulates this question: can we create a digital computer with enough storage, speed, and the right program to play the imitation game successfully? This universality concept is fundamental to computer science and demonstrates Turing's deep theoretical understanding. Here, Turing systematically addresses various objections to the idea that machines could think. He lists 6 major objections. 1. The theological objection. Thinking requires a soul, which machines don't have. 2. The heads in the sand objection. The consequences of machine thinking would be too frightening to contemplate. The argument from consciousness. Machines can't have genuine feelings or awareness. And he said, not until a machine can write a sonnet or compose a concerto because of thoughts and emotions felt. Arguments from various disabilities. Machines cannot be kind, they cannot be creative, they can't fall in love or make mistakes, etc. He comes with great counter-arguments against the objection that machines can't make mistakes. And then there's Lady Lovelace's objection. Machines can only do what we program them to do and not originate anything new. This is becoming increasingly arguable with modern AI implementations. For each objection, Turing provides thoughtful counter-arguments that still resonate today. These objections reveal the psychological, philosophical, and theological resistance to the idea of machine intelligence. Many of these same objections still appear in contemporary discussions of AI, showing how prescient Turing was. In his final section, Turing makes his most forward-looking suggestions. The highlighted text shows his proposal. Instead of programming an adult mind, program a child's mind that can learn. This insight anticipates modern approaches to machine learning by over half a century. Key points on the left reflect Turing's understanding that the child's brain is simpler and more easily modeled. Teachers often don't understand exactly how learning happens. Some people argue that modern neural networks act like black boxes. Random elements are important for exploration and avoiding getting stuck in problem solving. This is a crucial element in modern large language models. They use randomness for predicting the next word in a sentence. They don't always choose the most likely one. Then there's Turing's prediction that machines might eventually match humans in intellectual tasks. The right side shows modern parallels to Turing's ideas. Neural networks are inspired by the brain's adaptability. Large language models learning from vast amounts of text data. Reinforcement learning using rewards and penalties. Emergent capabilities not explicitly programmed that some might argue disprove the Lady Lovelace objection. The fact that a large language model can play chess and build a website, for example. Turing effectively predicted the shift from rule-based AI to learning-based AI that would occur decades later. His closing line in the paper, "We can only see a short distance ahead, but we can see plenty there that needs to be done." It reflects both humility and excitement about the future of the field. To close our presentation, let's reflect on Turing's extraordinary foresight. Written in 1950, before most of the fundamental developments in computing had occurred, he mapped out the conceptual territory for artificial intelligence. He provided not just philosophical speculation, but a concrete test, a clear focus on digital computers and realistic assessments of the challenges. His prediction that by the year 2000, machines might be able to fool an interrogator 30% of the time wasn't far off. Modern AI systems like GPT-4 and Claude would likely pass his test in many scenarios. And what's perhaps the most impressive is that Turing identified the key approach that would eventually prove the most successful: machine learning rather than rule-based programming. His paper reminds us of the value of clear thinking, intellectual courage, and the willingness to challenge conventional wisdom. Thank you.